Hello. In this tutorial, we would like to demonstrate the working of monostable multivibrator, and we are not intended to cover working theory behind it, but we would like to see how to simulate monostable multivibrator rather than theoretical part of it. So let's begin with. So we are trying to use Pspice 9.1 student free version. And this is how it looks. You can fit. Let me take. So this is part of ability enhancement course offered at VTU Belagavi. We have already covered 10 experiments. This is 11th. Let me take a Pspice timer. So you can go here and type Pspice timer. Okay. Then we want one resistor and two capacitors. Okay. Let me take R. I'd like to put it in this way. So let me fit so that you can see what I'm trying to do. First, what we do, we'll try to connect the circuit, and then we do the design, and we set up the simulation environment, and then we try to do the simulation. Okay, let's do it. See, put it here, and we want one more capacitor. Let's not try to change the values of it at this point of time. Okay, so 2 is trigger, 4 is reset. We need VDC for VCC, and we'll try to rotate it by shortcut Control R. So what I did now, I took VDC. So by default it is positive and negative, something like this. So you can keep it like this, nothing wrong in it. And then we can connect. Okay, nothing wrong in it, but I prefer to do in this way. Okay, 4 is reset and it is active low, so by default this must also go to, I don't want to reset in between, so let it go to the same point, that is VCC, and I need ground, G and D analog. I'm trying to connect it. Okay, then for this I just wanted to give, there is a range with which you can operate 555 timer. 5 volt is sufficient for us. You can extend up to say 10, 15, 18. I think there is a range given in the data sheet. You can extend up to that point, nothing wrong in it. Then we need ground, one more ground, so I'll simply copy and paste it here. And you can connect it to pin number 1. Next thing is, since it is monostable multivibrator, monostable means one state is stable, that is state 0. For a short moment of time it will go to an unstable state, to logic 1. In general, if I say logic 1, I should not say logic 1, say it is high, say VCC, for a short period of time. That period is decided by these R and C value, that is R1 and C1. The formula is there, that is TP is equal to 1.1 RC. You will see it later. So before that, let me finish the connection. Okay. So for monostable multivibrator, 6 and 7 must be shorted. It's clear. I just wanted to check whether it is recording or not. Yes, it is going nice. So this can be normal point, not 1 microfarad at 100 nano. Okay, let me put it in microfarad only. And this must go to pin number 5. Okay, there is no short. Just ensure that there is no short. There should not be any dot in this point. So these two values I have to decide it later. Let me do it a bit later. Okay. So next one is the remaining thing is a trigger. I have to trigger means I have to take pulse. So you can search for V pulse. Keep it here. So in between this R may come. So what I do, I'll pull this R bit up so that I can draw easily to the trigger, to the ground. Okay. So how much is the value of trigger? Excuse. How much is the value of these values? We'll see it later. Initially, let these things be 0. Okay. Anyhow, we'll do it later. And now output. Since I cannot keep it open in the practical, I can keep it open where probe itself can be a load. Now I have to give a separate load because it is a simulation. So this can be say 10K, or you can even keep it 10K or 100K or anything. Nothing wrong in it. So I have to connect probes here and here as well, and this one. Now I have to come to the point where I have to decide what is the value of R1 and C1. In turn, I have to decide what is the value of the pulse width, input pulse width, and period. So let me take a small text box here and let's say it as design. Put it here. So in this, I would like to extend this. Okay. Suppose if I take, I know the formula, that is Tp equal to 1.1 R into C. Here it is R1 C1 in this case. Now if I say given value of Tp is say 10 millisecond, if I take, assuming C as say 1 microfarad, then what is the value of R? R you have to find. So if I have these values, if I try to calculate, I am going to get R as nearly 9.09K or 9.1K. Okay, this I got. You just check and cross verify. So this must be now 1 microfarad rather than 1 nano. So I got it 1 microfarad. Okay, these two R1 and C1 will decide the TP. Now say if it is 10 millisecond, so these things, let me do it. By default DC 0, AC 0, AC component and DC components. V1 let it be 5 volt, V2 we make it 0, because anything below 1/3 VCC can trigger. Some people make it +5, -5, nothing, not needed, very much not, so anywhere between 1/3 VCC is going to be okay. You can even you can put V2 as 1 volt, still it is going to be working. Time delay, and at this point I don't want to give any delay. Rise time, say 10 nanosecond. Rise time and fall time, if you extend it, you can able to see the switch in the output exactly at 1/3 VCC. You can extend up to, say, even you can make it like 100 nano or something like that, so that you can able to see the switching exactly at 1/3 and 2/3 VCC. Okay, that's a good way to do it. Pulse width, you should give it less than 10 millisecond. Just ensure, this is the critical point. If you give more than 10 millisecond, it will continue to stay in the state high, so that must not be there. So pulse width, it should not exceed more than 10 millisecond, because our design is for 10 millisecond. So let me make it, say, 6 millisecond. Period must be greater than, again, as usual, I need not to say, let it be, say, 15 millisecond. So every 15 millisecond the pulse will repeat. Okay, let's do this. And in the analysis, I don't need bias point, anyhow these things will appear. I simply go for transient and say I want, say, 4 cycle or something like that. In that case, let me give, say, 50 millisecond, so that I can get enough number of simulations. Let me close and save. I already saved this one. If you have not saved, you save it in a proper location with a given name. So I have given meaningful name as Monostable. Let's me simulate it. Yes, this is how it looks in the simulation. There is nothing wrong in it. As soon as you see, better what I do, I'll delete one of this, or you can rename it if you want to get it clearly. The capacitor, here to here, if it is, say 15 millisecond to 25 millisecond, it will charge to 2/3 VCC. You can keep it 2/3 VCC. That means 10/3. That is 3.33. If you want, you can trace it. What is the level to which it is trying to do. Okay, let me select red one, and then I can see it. Okay, so it is going to 2/3 VCC, somewhere around 3.3 volt, and the blue one is the output, and the falling, the green one is the trigger pulse. For clarity, what we do, we'll try to rename the nets so that I can get, okay, sorry about that. So VP, if I say V pulse, that is the input. I am simply renaming. This is the voltage across capacitor, that is VC, and I would like to see that is out, say V out. So these things now clearly visible at the output side, so I don't have to do it. So since output is simply equal to the rise time, As soon as it reaches, it is going to switch during the falling edge of. So what I do, I'll simply take new window so that you can see the trace of these things. I am going to search it for V out. Okay, so not this one. V off, V out. This one. Okay. Sorry. Not. This is going to be. I take new window. Add a trace. No search for V out. Okay, now what I do, I'll keep these two parallel so that you can able to see the output here very clearly. V out, from this point I am trying to delete it. This is just for comparison purpose. Okay. So in the falling edge of the V pulse, negative edge, as soon as it is coming down, so this will be triggered. During that point, capacitor will start charging and it will reach to 2/3 VCC, that is 3.3 volt, and till that point the output will be high. As soon as it reaches, it is going to flip. Okay, if you study the internal structure of 555 timer, you will understand the working, and anyhow these things will be covered in the theoretical part, and the output will go down, okay, till the next cycle. Okay, as soon as it comes next cycle. So this must be 10 millisecond. If I simply see, this is say 15 milliseconds to 25 millisecond, it is 10 millisecond. What we designed is for 10 millisecond. Okay, this one, what we got is 10 millisecond. If you want to clearly see the outputs, what we can do is we can take a print screen and put it in Paint. Invert the colors so that you can see what exactly I was trying to explain. Okay, now the pink color one is the trigger when it is coming down, and when it reaches, if you increase the T fall and TR, you can able to clearly see when it is going to rise, when it is going to fall. Okay, so initial cycle you can ignore, and that can be done by simply going to here, the transient, no print delay, you can say some initial 10-15 millisecond you can avoid. Okay, by doing this you can ignore the first cycle. So this is it, and have fun while doing it. Thank you.